Hello everybody, today we'll talk about accelerometer directions. So what is an accelerometer? An accelerometer is an instrument that measures acceleration. Acceleration is the rate of change of velocity with respect to time. Velocity in turn is the rate of change of displacement with respect to time. Accelerometers are useful in detecting and measuring vibrations. If you want to learn more about accelerometer, you can check the link in the description below. So there are different types of accelerometers, such as uniaxial, triaxial. We're going to focus on triaxial accelerometer. So what is a tri-axial accelerometer? It's an accelerometer that can measure accelerations in all three directions, that is x, y, and z. So this is a schematic of a tri-axial accelerometer. You can see the namings, the x, the y, and z, and the other end you have this output that goes to the data acquisition system. So if you want to know how to properly figure out the direction an accelerometer is measuring, you need to start with the right hand thumb rule. So as the rule says, you need to use your right hand and align the three fingers, that is the thumb, index, and middle, in such a way that they are all perpendicular to each other. And if you align in this orientation, then each finger represents an axis, and the direction in which the finger is pointing represents the positive axis. So by convention, index finger is pointing the x-axis, middle finger represents the y-axis, and thumb finger represents the z-axis. And the direction in which the finger is pointing is the positive side of the axis. So let's look at it as a schematic. So let's say these are the three fingers of your right hand. So let's say this is the thumb finger, and this is the index finger, and this is the middle finger. So by the right hand thumb rule convention, so the thumb finger is representing the z-axis, the index finger the x-axis, and the middle finger the y-axis. And the direction in which the finger is pointing represents the positive side of the axis. So let's say if you align your right hand thumb rule in this orientation, your thumb is going to point upward, and that up direction is the positive z-axis, whereas the down represents the negative z-axis. The same way, the index finger is pointing straight ahead into the plane, so that represents the positive side, whereas the other side is the negative. And the same way for middle finger, if it's pointing toward the left, so that's the positive, and right is negative. So we'll use this convention to determine what accelerometer and what directions the accelerometer is actually measuring, because it's easy to put the accelerometer in such a way that it always measures positive x, y, and z. But then the problem arises when you don't have enough space to paste the accelerometer in that particular orientation, and you have to make a compromise pasting accelerometer in any direction available, and then use this right hand thumb rule to determine what exactly the accelerometer is measuring. Alright, so now we'll look at 5 different positions and determine what exactly the accelerometer is measuring in those different orientations. So in this schematic, in the middle, I have the picture of the accelerometer in a particular orientation. On the right, I have the right hand thumb rule always available for display, so that we can use this to determine what exactly the accelerometer is measuring. And on the left side is the actual directions, or the answer for this particular orientation of the accelerometer. So this is the first orientation. It's a simple orientation. So in this case, as you can see here, you can see the Y side, the Z side, and you can see this output pin. And the X side is actually hidden. It's on the other side, the diametrically opposite side of this pin. So if I look at this right hand thumb rule, I can see that the X is actually measuring the positive X, Y is measuring positive Y, Z is measuring positive Z. So this is a trivial case, and the answer is X, Y, Z. All are measuring positive directions. So this is a good case, but not always we get this liberty to align the accelerometer in this orientation. So there are other complicated orientations based on the available space. So this is the second orientation. So as soon as you see this accelerometer, always look at the right hand thumb rule, so as to compare what exactly is this particular direction measuring. So in this case, it looks like the accelerometer has been rotated, but then I've not rotated the letters so that it's easier to visualize. So in this case, we can see that X is pointing to the left, so X is in line with the positive Y direction of the right hand thumb rule, which means X is literally measuring positive Y. Y is actually coming out of the plane, but it's actually along the x-axis, but not in the direction of positive X, so it's opposite to that, so it's measuring negative X. And Z has no change at all. It's still pointing in the up direction, so it's positive Z. So this is the next orientation. Again, let's look at this orientation and compare with the right hand thumb rule. So we see that y is pointing in positive y, so y is same. X is pointing upward. Actually, in right hand thumb rule, z is positive z is pointing upward, so which means that x is measuring positive z, and z is along the x-axis, but it's opposite to that of positive x, so z is measuring negative x. So there we have the configuration. So this is the next orientation. Again, let's compare it with the right hand thumb rule. We see y is measuring positive y, and x is along the x-axis, but it's opposite to that of positive x, so it's negative x. And z is not visible here, but it's on the diametrically opposite side, so it's actually along the z-axis, but it's not pointing upward, so it's pointing downward, and hence we have z as negative z. This is a complicated orientation. In fact, when you have this orientation in real life, you can actually see on the other side what directions are visible. But in this case, accelerometer is a cube, so a cube has only 6 faces. So out of the 6 faces, we can actually see the 3 faces. The one is the output, and the other 2 faces are blank. But on the other 3 sides, we have these 3 directions hidden. So in real life, as I mentioned, you can actually see what is on the other side, so have seen. So based on that, I can draw the conclusion. So I can say that z is actually on the bottom side. So z is along the z-axis, but it's actually on the bottom side, so it's measuring negative z. Y is on this hidden edge, so y is still along the y-axis, but it's measuring to the right, so it's negative y. And x is on the other side of this pin, so it's still aligned in the same x-axis, and also it's pointing toward the positive x, so it's positive x. So those are the directions, 5 different orientations. So what will happen if you make a mistake in the directions? What will happen? So let's say you conduct a measurement and you have made a mistake in this direction convention, and you're still going to end up measuring the accelerations, but when you process, the problem begins. So if you're only going to process the magnitude, that is, you're going to take like the average of all the directions and represent one single acceleration, well, probably you're not going to face any issues, because you're summing up all the accelerations and you're just viewing it as one single acceleration, which is still accurate. But if you want to see each and every direction, the contribution, that's where you're going to face the error. For example, if x-axis of a particular component was having more vibrations, and if you made a mistake, you're going to see some other directions as having more vibrations, which is not true. Especially if the goal is to detect mode shapes, which is very important to see the animations of how the part is vibrating in what particular direction. This would pose a erroneous result. So it's important to focus on the direction so as to get accurate results, especially in mode shapes or in areas where you want each and every axis individually. All right, thank you for watching this video. I hope you enjoyed it. Have a great day.